Rocks are alive. Not like breathing, but moving, changing, eating each other. Okay, that last one's a stretch, but only barely. Here's what nobody tells you in school. The ground you're standing on right now is not solid. It is not stable. It is not permanent. It is a thin, cracked shell floating on a planet that is actively trying to rearrange itself every single day. And geology, the science of all of that, is basically the story of a planet that cannot stop moving even after 4.5 billion years of trying. And trust me, you'll want to stick around to see just how chaotic this cosmic journey gets. If you want to keep uncovering the wildest secrets of our restless planet, make sure to subscribe so you never miss a video. So let's start at the beginning. Actually, let's start even before the beginning. Before there was Earth, there was just a cloud. A massive spinning cloud of gas and dust left over from an exploding star. That cloud started collapsing under its own gravity, and most of the material fell inward and became the sun. But some of it, the leftovers, the cosmic crumbs, started clumping together. Rock hitting rock. Dust sticking to dust. Over millions of years, those clumps got bigger and bigger until one of them was big enough to be called a planet. That planet was us. 4.5 billion years ago. Baby Earth. Now here's where it gets wild. Wah. The early Earth was not the pleasant blue marble you see in NASA photos. It was a nightmare. A molten, churning, constantly being bombarded by space rocks nightmare. The entire surface was basically a global ocean of magma. And because Earth was so hot and so big, something incredible happened. Everything sorted itself out by weight. The heaviest stuff, mostly iron and nickel, sank toward the center. The lighter stuff floated toward the surface. This process even has a name. It's called differentiation. And it's why Earth has layers, like a gobstopper from Willy Wonka. Except the center is iron, and the outside wants to kill you. So what are those layers? Imagine slicing Earth in half. Right in the middle, you've got the inner core, solid iron. Roughly the size of the moon. Temperature? About 5,000 degrees Celsius. That's roughly as hot as the surface of the sun. But, and this is the part that sounds wrong, the inner core is solid, not liquid, even at that temperature. Why? Because the pressure is so intense, 3 million times atmospheric pressure, that the iron atoms literally cannot move around enough to become liquid. They're just vibrating in place, screaming internally, but staying put. Surrounding the inner core is the outer core. Same iron-nickel composition, but here the pressure is slightly lower, so the metal is molten. Liquid metal. And that liquid metal is spinning and convecting, hot stuff rising, cooler stuff sinking, and that movement generates electric currents, and those electric currents generate Earth's magnetic field. The invisible force field protecting us from solar wind and radiation. No outer core doing its little liquid metal dance. No magnetic field. No magnetic field? Radiation strips our atmosphere. No atmosphere? We're Mars. So honestly, shout out to the outer core. Real one. Above the outer core sits the mantle. This is the big one. The mantle makes up about 84% of Earth's total volume. It's mostly rock silicate minerals, if you want to get technical, and it goes from about 30 kilometers below your feet all the way down to 2,900 kilometers deep. And here's the thing about the mantle that blows most people's minds. Whoa. It is technically solid rock. Technically. But given enough time, millions of years of time, it flows. Like extremely slow, extremely hot silly putty. If you punched the mantle, it would shatter. Like a solid. If you waited long enough, it would ooze. Like a liquid. Scientists call this property viscoplastic behavior. You can call it rock that doesn't know what it wants to be. And then at the very top, the part we actually live on, is the crust. Earth's crust is absurdly thin compared to the rest of the planet. If Earth were the size of an apple, the crust would be thinner than the apple's skin. Under the oceans, it's only 5 to 10 kilometers thick. Under the continents, up to 70 kilometers in the thickest mountain ranges. But thin as it is, the crust is where everything we recognize as geology actually happens. Earthquakes, volcanoes, mountains, canyons. All of it happening in this thin, fragile, broken up shell. And yes, broken up. The crust is not one solid piece. It is cracked. Fractured into about 15 major pieces called tectonic plates. And those plates, sitting on top of the slowly flowing mantle, are moving. Right now, as you watch this. Your continent is drifting at roughly the speed your fingernails grow, which sounds slow and unimpressive until you realize that given enough time, that speed rearranges every single continent on the planet. Which brings us to the question that no respectable geology video can avoid. If the continents are moving now, where were they before? About 300 million years ago, all the continents were one massive supercontinent called Pangaea. And yes, it looked exactly as weird as it sounds. Imagine South America and Africa just snapped together like puzzle pieces, because they literally were puzzle pieces. Antarctica was hanging out near the equator. India was vibing next to Madagascar. It was a completely different planet, wearing the same sky. Alfred Wegener figured this out in 1912. He noticed that the coastlines of South America and Africa match up suspiciously well. He noticed that the same species of fossils, plants and animals that couldn't have swum across an ocean, were showing up on opposite sides of the Atlantic. He noticed that the same distinctive rock formations appeared in Brazil and West Africa, like a torn page where both halves have the same sentence running across the rip. So he proposed that the continents had once been connected and had drifted apart. The scientific community's response? N. They clowned on him, relentlessly, for decades. Because at the time, nobody could explain the mechanism. What force could possibly move an entire continent? N? The answer, discovered fully only in the 1960s, was the mantle. That slow-flowing, silly putty rock we talked about. The mantle moves in giant convection cells. Hot rock rises from near the core, moves horizontally near the surface, then cools and sinks back down, like a very, very slow lava lamp that runs on geologic time. And the tectonic plates sitting on top of that flowing mantle get dragged along for the ride. That's it. That's the engine. 4.5 billion years of volcanic heat slowly churning the interior of the planet, and the crust just goes wherever the mantle tells it to go. Continental drift isn't some mysterious exotic phenomenon. It's a pot of water boiling in slow motion, with continents on top. Now here's where it gets spicy, because tectonic plates don't just float peacefully around like bumper cars in a polite kiddie ride. They crash into each other. They slide past each other. They pull apart from each other. And every single one of those interactions produces a different kind of geological disaster, or masterpiece, depending on your perspective. When two plates collide head-on, what geologists call a convergent boundary, one plate gets shoved under the other in a process called subduction. The plate diving downward melts as it descends into the hot mantle, and that molten rock, that magma, has to go somewhere. So it rises. It punches through the crust above it, and it erupts. That's a volcano. The entire Pacific Ring of Fire, the most volcanically and seismically active zone on Earth, a horseshoe of geological chaos stretching from New Zealand up through Japan, through Alaska, and down through the west coasts of the Americas, is a direct result of tectonic plates diving under each other and melting into the mantle. Mount St. Helens, Mount Fuji, Krakatoa, all of them, plate tectonics throwing a tantrum. But when two continental plates collide, not one diving under the other, but two equally thick, equally buoyant pieces of crust just ramming into each other, neither one sinks. So what happens? They crumple, like a slow-motion car crash between two semi-trucks where neither one yields. The rock buckles and folds upward. It builds mountains. The Himalayas, the tallest mountain range on Earth, home to Mount Everest, formed because the Indian subcontinent, which spent about 100 million years drifting north after breaking off from Pangaea, finally crashed into Asia. India didn't stop. It kept pushing. It's still pushing today. The Himalayas are still growing. Slowly. Fingernail speed. But growing. Okay, but here's where your brain needs to pause for a second. Because we just casually walked past something genuinely deeply insane. Wow. The rocks at the summit of Mount Everest, the highest point on Earth, 8,849 meters above sea level, are marine limestone. Limestone that formed at the bottom of an ancient ocean full of fossilized sea creatures, shellfish, tiny marine organisms that lived and died in tropical shallow water. Those rocks are now the highest rocks on Earth. The peak of the highest mountain on the planet is made of ocean floor. An ancient sea called the Tethys Ocean closed as India crashed into Asia and its floor got crumpled upward and pushed to the top of the world. The summit of Everest is technically ancient seafloor. Stop for a moment and actually feel that. Meanwhile, on the other side of the tectonic interaction menu, divergent boundaries, where plates pull apart from each other. Magma wells up to fill the gap, creates new crust, and slowly spreads the seafloor outward. This is literally called seafloor spreading, and it's happening right now under the Atlantic Ocean. The Mid-Atlantic Ridge is a massive underwater mountain range running down the center of the Atlantic, and it's the seam where North America and Europe are pulling away from each other at about 2.5 centimeters per year. The Atlantic Ocean is getting wider. Slowly. But wider. And then there's the most cinematically unsatisfying interaction, transform boundaries, where two plates just grind sideways past each other. No mountain building. No volcanoes. Just two massive slabs of rock slowly sliding in opposite directions, locking up with friction, building stress over decades, and then suddenly, violently, releasing all that stored energy at once. That's an earthquake. The San Andreas Fault in California is the most famous transform boundary in the world. Los Angeles is slowly moving north toward San Francisco. In about 15 million years, they'll be neighbors. Nobody tell the real estate market. So we've got plates moving, continents crashing, volcanoes popping off, mountains being born from ocean floors. All of this geological chaos is producing one thing in enormous quantities: rock. Different kinds of rock. Rock that forms in completely different ways, tells completely different stories, and looks completely different from each other. And this is where most geology classes lose people, because suddenly there's a lot of memorization and Latin, and nobody explains why any of it matters. So, let's fix that. There are 3 types of rock. 3. That's it. And the difference between them is simply the story of how they formed. The first type is igneous rock. Igneous comes from the Latin word for fire, which is exactly what it sounds like. Igneous rock is rock that used to be magma and then cooled down and hardened. When lava pours out of a volcano and cools fast on the surface, you get fine-grained rock like basalt, the most common rock on Earth's ocean floor. When magma cools slowly deep underground over millions of years, you get coarser rock like granite, the stuff kitchen countertops are made of. Same basic origin, completely different texture just because of how fast it cooled. Granite is basically lava that was patient. Second type, sedimentary rock. This is where things get detective-like. Sedimentary rock forms when tiny particles, sand, silt, clay, the broken remains of other rocks, the shells and bones of dead organisms, settle in layers and get compressed over time until they turn to stone. Sandstone. Limestone. Shale. These rocks are geological archives. They record what the environment was like when they formed. Ripple marks in sandstone? N. Ancient riverbed. Fossils of coral? N. Ancient reef. Those marine limestones at the summit of Everest? N. Ancient ocean floor. Every sedimentary rock is a page in Earth's diary, and geologists are the ones who can read it. Third type, metamorphic rock. Metamorphic rock is rock that was one thing and then got subjected to extreme heat and pressure, Not enough to melt it completely, just enough to transform it, and came out the other side as something different. Marble is metamorphic. It used to be limestone, the same stuff full of seashells, but then it got buried deep in the crust, pressure and heat worked it over for millions of years, and it came out as the beautiful crystalline stone that fancy floors and Michelangelo sculptures are made of. The Pietà in the Vatican is carved from ancient seashells. Geology does not lack for plot twists. Now, you've probably heard the word mineral used interchangeably with rock your whole life. Same thing, right? And wrong. Very wrong. And this is one of those distinctions that sounds pedantic until you realize it actually matters a lot. A mineral is a naturally occurring, inorganic solid with a specific chemical composition and a crystal structure. Every mineral has a defined formula. Quartz is always silicon dioxide. Halite, table salt, is always sodium chloride. Calcite is always calcium carbonate. Change the formula, change the mineral. A rock, on the other hand, is an aggregate, a mix of one or more minerals. Granite, for example, is a rock made of 3 minerals: quartz, feldspar, and mica. Granite is to minerals what a burrito is to ingredients. The burrito is not the rice. The burrito contains the rice. Here's the Hank test. You know Hank Schrader from Breaking Bad? N. DEA agent, excellent at his job, obsessed with minerals. There's a legendary scene where someone calls his collection rocks, and he says, with full offense taken, "They're minerals, Marie." And honestly, N. Hank was scientifically correct. He was being pedantic in the middle of a family meltdown, yes. But technically right. If Hank showed you a chunk of pure quartz and you called it a rock, you'd be wrong. It's a mineral, single compound, definable crystal lattice, specific properties. If he showed you a chunk of granite, okay, that's a rock mixture of minerals. The distinction matters because minerals are the ingredients. Rocks are the recipes. And geology is the cookbook. Which brings us back to the beginning. Back to that thin, cracked shell we started on. Because here's the thing. Everything we just covered, every layer, every plate, every volcanic eruption, every mountain range, every grain of sand on every beach, it's all one system. Rock forms, moves, gets subducted, melts, erupts as lava, cools, gets eroded into sediment, gets buried, gets compressed, gets metamorphosed, gets uplifted, erodes again. The rock cycle. It's been running for 4.5 billion years, and it never stops. The ground under your feet right now has been through that cycle multiple times over. What was once the floor of a vanished ocean will someday be lava. What is now lava in Iceland will someday be a beach. The planet is not a static stage for life's drama. It is a character. It has been changing this whole time. Pangaea broke apart. But before Pangaea, there was Rodinia. And before that, other supercontinents we barely know the names of. And the models say that in 200 to 300 million years from now, the continents will converge again. There will be another Pangaea. Pangaea Ultima, some geologists are already calling it. The Atlantic Ocean will close. The Americas and Europe and Africa will collide. New mountains will rise from the ruins of the current ones. But here's the question nobody has fully answered. And it's not a small question. It's maybe the biggest question in planetary science. If tectonic plates are what makes Earth geologically alive, if this constant churning and recycling of the crust is what regulates our climate, enables volcanic activity, and creates the mineral-rich environments where life can thrive, then why does Earth have plate tectonics at all? And because Mars doesn't. Venus doesn't. The Moon doesn't. As far as we can tell, Earth is the only rocky planet in the solar system with active plate tectonics. Something about Earth's size, its water content, its thermal history produced a planet that moves. And we still don't fully understand why. We live on the one planet in our solar system that can't sit still. And we have absolutely no idea why we got so lucky. If geological activity is the literal engine that keeps our planet habitable, does that mean finding complex alien life on a geologically dead world is flat out impossible? Or are we just a weird cosmic fluke? And drop your wildest theories in the comments below. And if you haven't already, make sure to subscribe so you don't miss our next deep dive into the cosmos.